So I'm going to define oxidation numbers. Now, you already know what they are, we just haven't called them oxidation numbers yet. So what oxidation numbers are, the charges that exist on the monatomic ions. So when we said that barium, since it's an alkaline earth metal, it's always going to form a +2 charge. That +2, that's its oxidation number. So it's just the charges on the ions. They're also called oxidation numbers. These are the numbers that each atom fulfills to gain its full octet. And we talked about that when we discussed isoelectronic atoms in Chapter 2. To determine what those charges should be, all you need to know is how many electrons is that particular atom need to gain or lose to have a noble gas configuration. So we've looked at these charges on several occasions. These are the charges of the main group elements that form for every element in that group. The octet rule says that everybody wants 8 electrons. They all want to be a noble gas. Of course, there's always exceptions to that rule, being hydrogen and helium. They can only have a max of 2 electrons. The rest of the atoms on the periodic table of the main group elements want 8. In this diagram, the numbers above are the number of valence electrons of each element on the periodic table. We use these numbers of how many valence electrons they have so that we can figure out how many they would like to lose or gain to become a noble gas state and have a full octet. Alkaline metals like to have an oxidation number of +1, so they like to have a +1 charge. Well, why is this? It's kind of a review from Chapter 2. They're a metal, so we know they like to lose electrons. Since the alkaline metals only have 1 valence electron in their outer shell, they lose that 1 valence electron to have a full octet. What that means is, notice I have the electron configurations of lithium and sodium pictured here. You can see that in their outer shell, they each have just 1 electron in that s orbital. So when they lose that 1 s electron, they now have a noble gas configuration. So looking at this example, the lithium +1 ion will now have the same electron configuration as helium. So both of their electron configurations will be 1s2. Sodium, when it loses that 1 electron, now has a noble gas electron configuration the same as neon. 1s2, 2s2, 2p6. Notice that it will have 8 electrons in its outer shell. Its outer shell being all the electrons in level 2, period 2. The electrons being these superscripts here. So 2 plus 6 tells me there are 8 electrons. So now sodium is happy. Potassium, the example also shown here. So we're looking at the electrons in the 3 level. Potassium loses 1 electron. It is now isoelectronic with argon and has the same electron configuration as argon. Alkaline earth metals. Notice all the alkaline earth metals have 2 valence electrons in their outer shell, represented by these 2 electrons in the s orbital. So if they lose those 2 electrons, they now will have 8 and have the same electron configuration as the noble gas in the row above them. Halogens, they are nonmetals, so we're going to see them gain electrons. Why are they gaining electrons? Because they're trying to get 8 electrons. So if you look at their outer shell, in the case of chlorine here, we have 3s2, 3p5, so that would be the outer shell, the level n equals 3, for the principal quantum number of chlorine. The electrons it has are 2 in the s and 5 in the p. That gives me a total of 7 electrons. Well, since chlorine wants 8 electrons, it's going to gain 1 electron. To have 8, that means it's happy. So fluorine, when it gains 1, is now isoelectronic with neon because they have the same electron configuration. The same applies for chlorine, bromine, and iodine. They are isoelectronic with the noble gas in the same row. So let's see how this looks. In this example, I have shown a sodium atom. Now, a sodium atom has 11 electrons. If you do its electron configuration of a neutral sodium atom, you will count 11 electrons. Now notice this outer shell in pink here has just 1 electron because sodium is an alkali metal and just has 1 electron in its valence outer shell. So what happens is it wants to have a full octet, a full outer shell. So when it loses that 1 electron, notice now the pink shell is gone. Notice also that sodium now has a +1 charge because it lost 1 negatively charged electron. But its outer shell in blue now, if you count those electrons, you'll see that there's 8 on that blue level because it now has a full outer shell. So it has a same electron configuration now as a neon atom. Now let's look at chlorine. So chlorine, in its pink outer shell, has 7 valence electrons when it's neutral. When it gains 1 electron from sodium, for instance, it will now be negatively charged because it gained 1 negative electron, and it now has 8 electrons in its outer shell, the same that argon, the noble gas argon, has. Last but not least, we're going to look at the properties of ionic versus covalent compounds. So ionic compounds are crystalline structures. They're generally solids at room temperatures, and their melting points and boiling points are higher than covalent compounds. This is due to their crystal lattice. There's a lot of stacking with these ions, creating lots of interactions. For example, sodium chloride, also known as table salt, it has a melting point of 801 degrees Celsius. We're going to do a lab on a hydrate, an ionic compound, and we're going to be heating that compound up with a Bunsen burner. The reason we can do this without destroying the compound itself is because of the high melting points of ionic compounds. With solutions of ionic compounds, if they're soluble in water, you'll often see that the ions will separate into the positive and negative cations and anions. This causes solutions of ionic compounds to form electrolytes. And these electrolytic solutions can actually conduct an electric current. And we'll talk about this more in detail in later chapters. Here's a picture of the crystal lattices of ionic compounds. So all of these purple spheres, if this were an ionic compound of sodium chloride, the purple spheres are sodium plus ions. The green spheres are chlorine minus ions. So due to this intricate stacking, it creates a very stable structure, making it very hard to break apart. Case in point, high melting point. Now let's explore the properties of covalent compounds. So covalent compounds can be solid, they can be liquids, they can be gases, combination. So we're looking at compounds that share electrons. The melting points and boiling points are often lower than ionic compounds. Notice an example here, methane, CH4, or carbon tetrahydride if you're naming it systematically, has a melting point of -182. Thus making it a gas at room temperature. Note, there are always exceptions though. One of the exceptions for covalent compounds being silicon dioxide, which is quartz, a very hard high melting point solid. If a covalent compound is soluble in water, it does not break apart into ions since they are sharing electrons. There's no transfer, so no ions exist. These are therefore going to form non-electrolytic solutions. They will not conduct electricity. An example of this would be sugar water. Sugar does dissolve in water, but since it's a covalent compound consisting of carbon, hydrogen, and oxygen, you will not see any ions in the solution.